Our client was the NanoProduct Lab, established by Dr. Mustafa Badoui in the fall of 2016. The lab's primary focus is in experimental research in nanoscience, biotechnology, and manufacturing engineering, with the goals of creating solutions that impact societal challenges in energy, healthcare, and the environment. Currently, the productivity of blade casting systems is limited due to the slow rate and low quality coverage of lab-scale blade casting systems. By designing a scalable and modular roll-to-roll blade casting system, the continuous production of nanoparticle-coated flexible film will be made possible. Our goal is to design a scalable and modular roll-to-roll blade casting system with the ability to coat Kapton film with nanoparticle solution continuously while allowing for future changes to be made to the system. The blade casting process begins with nanoparticle solution being deposited on Kapton film. The film then passes under a blade, which evenly spreads the solution over the surface of the film. The film is then heated, causing the solution to dry and leaving an even coat of nanoparticles over the surface of the film. By incorporating a roll-to-roll system to this process, the continuous coating of film becomes possible. The roll of Kapton film starts on the leftmost roll-to-roll module and is pulled through the system by the motorized roll-to-roll module on the right. The tape then travels upwards to the first tension rod, which is level with the surface of the substrate module in the second tension rod. The dispenser module applies the nanoparticle solution to the film, which then passes under the blade module, which evenly spreads the solution over the film surface. The film is heated as it passes over the substrate to dry the newly spread solution. The film moves to the second tension rod, then down to the second roll-to-roll module where it is rewound. This is the blade module. Its purpose is to hold the blade at a steady 20-degree angle 50 micrometers above the tape as it passes over the substrate module. This angle and distance allows for the highest coverage of solution on the Kapton film. The blade module must also be able to move in the X and Z directions. To meet these requirements, a blade mount was designed and attached to a rotational translation stage. This rotational stage was then attached to an XY translation stage and turned on its side to move in the X and Z directions. This stage was then mounted to a backboard, which was then attached to a kinematic base and mounted to the breadboard.
The substrate module provides a flat surface to support the film underneath the blade. It also features a heating element to speed up the crystallization process for increased productivity. The L-shaped design provides a flat support for the film while using the least amount of materials possible. Aluminum will be used as it is lightweight and cost-efficient. Key features include adjustable height and M6 size slots on the bottom of the L bracket to easily attach to either kinematic base or the breadboard itself. For the heating element, we chose a thin, flexible heater with adhesive backing to easily stick to the bottom of the substrate's surface. Thermocouples will measure the temperature of the film, and a temperature controller will be attached to allow the temperature to be adjusted from 0 to 80 degrees Celsius.
The dispenser module's purpose is to apply even coverage of the solution to the film before it passes under the blade module and substrate. This module is composed of an infusion syringe pump that uses a 21-gauge blunt-tip needle to attach to microfluidic tubing. The tubing has an inner diameter of 750 microns and must dispense 6.35 milliliters of solution per minute. The infusion pump is compatible with syringes ranging from 3 to 100 milliliters. For our design, we will use a 3 milliliter syringe for testing and a 20 milliliter syringe to coat the entire 50-foot roll of Kapton film.
These images depict the roll-to-roll module. The requirements of this module were that it must be able to hold 1 to 2 inch width films, maintain a constant speed within a range of 1 micron per second to 1 millimeter per second, and provide tension to the film throughout the system. The unwinding roller module pictured on the left is the starting point of the system. A braking mechanism was designed to ensure constant tension on the film, despite the amount of film on the unwinding roller diminishing as the process takes place. The winding roller module, pictured on the right, is the endpoint of the system. A stepper motor is coupled with the winding roller and is the primary source of movement in the roll-to-roll system. The motor pulls the film through the system at a constant velocity between 1 micron per second and 1 millimeter per second, while satisfying the roll-to-roll requirement of the project.
This decision tree outlines the thought process we followed when selecting parts for our module designs. Once the specifications for each module were defined, a list of parts was compiled for vendor comparison. The prices and dimensions of each part were compared to find the optimal fit. Price was an important factor in part selection, but the cheapest option was not always chosen to ensure a high level of precision was met. In order for a part to be finalized, it would need to satisfy its module's design requirements at a justifiable price point, fit the dimensions of the module in SOLIDWORKS, and gain client approval.
After comparing the price and quality of different vendors and making our final part selections, the total cost of parts for each of our modules and miscellaneous pieces such as the breadboard comes to $2,380.15 plus the cost of machining parts in-house. Other roll-to-roll systems on the market would cost several $1,000s more.